Okay. So I'm speaking exactly of pulsation in closed binaries, so we try to convince you that it is worth to analyze this data, and in spite of the fact that they're more complex, of course. And actually we'll essentially speak of one case study because I don't have much time and I think it's explicative. So this is my preferred view of the photometry revolution that we know. Before CoRoT, that was a system known, observed before. And that here you see the same as observed by CoRoT a few years later. And of course, we have an enormous gain in terms of observed points and in terms of accuracy and monitoring and everything. And also in terms of complexity of the analysis. You have already seen the incredible zoo that has been found of binaries with pulsating, so I go through this, different type of pulsators in eclipsing binaries. And how do you handle this? Normally what has been used is in iterative procedures. And this works with, actually, you have several steps, masking first the eclipses, for instance. Then you have alternate subtraction of the harmonic and the fit of the binary fit. So you get, from the original light curve, you take out the harmonic fit, you get the eclipsing binary signal, you model that, and then you subtract it, and you get a better approximation of pulsation, and so on. Typically with standard methods like Fourier transform, nonlinear fit, period 0, 4, Phoebe for the binary, and so on. The bad news is that this works, but this works in some conditions, like the magnitude of the two phenomena should be possibly different. Otherwise, you will get in trouble. I'll show you the typical case. This is a CoRoT, a Kepler binary, KIC385884, and it's a binary with, it's been observed for more than 1,000 years, both in long and short cadence. And it's a perfect situation where the previous method does not work. If you look here, you see the pulsation, and you see the, let's try to use this. You see the pulsation, and you see the eclipses that are heavily deformed by pulsation. And here you see these two typical, say, frequency, these are frequencies in the range of delta Scuti, and the system is eccentric. Okay, when you use the previous method I mentioned to you, if you put the light curve in phase, here you will see okay, you do the subtraction, and this improves the primary minimum. You take out the pulsations, but the secondary minimum gets worse. Why that? Because actually this is the eclipse of the pulsating star. We are taking out the same pulsation everywhere, and that is not correct. And this creates residuals and problems in the following analysis. So what actually you have to do is to a first order correction, in which, at least first order, in which you weight the pulsation with the fraction of light that is comes from the star under eclipse, under the pulsator. The other question in this case is that you are having an elliptic orbit. And this means that you have a bump here. So if you take out all the frequencies you find, what happens? And that you are doing something wrong because some are produced by this bump. So you have to keep some orbital overtones. By simulation, I've seen here that is up to 15 orbital overtones. Otherwise, again, you get in trouble. But if you do that, then you get this cleaned by pulsation, from pulsation light curves, and you get an excellent fit, apart from some deviation in the minimum. And so you are happy with the solution of the light curve. To this, one has to add the spectroscopic observations. So we took a lot of spectra. There was a long campaign here. We took a lot of spectra with different instruments. And this gives you radial velocity and also atmospheric parameters. And when you look at the radial velocity curve, this is primary, this is secondary. You see scatter here, but the stars have the same luminosity. So this actually is pulsation. And doing the analysis of the residual, we got these two frequencies that are exactly the same from photometry. And when you take it out, you get much better fit. And you have an extra bonus. You see here, this is the Rossiter effect. And you can combine the effect that the star, this is the pulsating star, and this, the Rossiter effect, tells you that this is eclipsed at phase minus O2. So this is the secondary star. So having the binary in this effect, you can again confirm which star has the, say, is the pulsator, or at least has the highest pulsations. What else? You have now the model of the binary you derive with precision masses, and you get the formation that is an elliptic system, quite elliptic, with it's eccentric, with similar masses, very similar, but different temperature and different radii. So there is one of the components, the primary, should be slightly evolved. Then other thing we did, you can do, is to try to extract information from the pulsation and through the pulsational analysis. So this is the what just you get from CASOC with the binary. This you cannot use as it is, of course, but you take out the binary, you get a much better, of course, frequency spectrum, and you see frequencies in this range from 0.3 to 20 days almost. This is a blow up of this region after a pre-whitening of the highest frequencies. And doing detailed analysis, we found these frequencies here. I list just the first to show you that there are in the range 7, 10, and then there is some also here in this part at lower frequency. And for the detailed analysis, this is the in the high frequency variability, and there you see that for some modes, that was a work of Jembowska and Krolikowska. Actually, these modes of equal 1 are trapped in the envelope, and so they are less coupled to G modes that are in the interior, and have a higher probability to be excited, and so to be at observable frequencies. And as these non-radial modes are closer for a low L to the radial modes, you get some preferred spacing. And this can be used. We were looking at the frequency difference of all our 400 frequencies, and we did found, this is for the first 100 frequencies, this is for the full 400, we did found a sign of preferred spacing. This has been used, for instance, to derive the gravity, because you can put this in a plot built with models where you have the lowest, the frequencies of the lowest radial mode, and here you have the difference. And then you have this grid with the gravity. But in our case, we can do the opposite. We have the gravity from the binary. So I can use this plot to put the spacing I find and the gravity I know, and then I derive what is, for instance, the frequency of the fundamental mode here, and this looks to be 7.5. So this is exactly around the second frequency we found. So we can tell that this is the fundamental radial mode, and the other frequency is the non-radial mode being lower value. So this comes from also from the binary parameter. Then if we go to the low frequency variability, then we had also some frequency found here, significant frequency, several. And if we look here at the, these are we were asking ourselves if these G modes were high order G modes. As in that case, if we were studying an hybrid gamma Dor delta Scuti star. And if this applies, then you have this classical relation, because you are in the asymptotic regime between the frequency, the spherical degree, and the order of the mode, and the integral of the Brunt-Weiss frequency in the cavity. And from this classical relation, descends this relation between the frequency ratio and the order of the mode. These are not strongly dependent on n. So finally, it's very simple between the frequencies of a given mode pair and the radial order. So what we did was to select the highest frequency here and try to see if they respected these combinations. Well, the result is this. Actually, when you do that, we found a list of possible combinations that were following the relation, and with different value of the Brunt-Weisler integral that was being a binary was computed assuming L equal to 2, because it is more likely to have this type of frequency modes excited. But I will show you that thanks to the binary and the comparison with the evolutionary models, okay, we will be able to tell which one is better in this long list of combinations. So let's go to the comparison with models. Comparison with models was made using a very fine grid around the component mass derived from the binary model with class, that is the evolutionary program of Kepler et al., and with these ingredients here. Models were done both with and without overshooting, and for different chemical compositions. Then, what we did was to keep only the pairs, because it is a binary, so you should have the same age, the same composition, and we took the masses and the radii that were derived from the binary model, and the difference of temperature, because this is the Sounder value you get, not the individual temperature from a single color light curve, so this difference. And we kept only the models that were respecting this, with different chemical composition. Then if you take from spectroscopy the temperature of the primary, you are left with this group, primary and secondary. So this is the age of the system. Not quite simple, the classical system. Now, let's go back to the second. In this case, with this age, I'd go and these are the value of the Brunt-Weisler integral that I was showing before in the table. And these are from models. If I take that age, and this is only for the secondary because the value for the primary is much higher. If I take this age, I get these good values. And these are very similar to the two values that I was highlighting in the previous slide from the combination. So in this way, I can choose some of the combinations. Now, look at the excited frequency in the delta Scuti domain. I have this age, primary and secondary. This is the observed range. These are the models that are chosen. And this is a very good agreement with what is observed. This is maximum and minimum, so you are in the middle, it's okay. And then the last, in the gamma Dor domain, you have the same play. Here is the age. This is for the secondary because for the primary, the mechanism is not a Borg. And then you get this interval, and this is what is observed. So it fits in quite well. And so let's go to conclusion. I've forgotten to tell, all the pulsations, the excited pulsations were computed with the MAD code by Marc-Antoine Dupré, the code. And the conclusions are that, okay, when you have a binary and you have pulsation, it's more complicated. From each of those, you can derive some information. From here, the masses and radii, you can read the list, identifying the pulsating component. With models, you can derive the system age and select parameters. On the other side, and we have something I didn't mention here, but this is FM stars, the orbit effect I was speaking before. Again, you can partially identify the mode with the help of the binaries, estimate the Brunt-Vasala integral, but when you put the things together, conclusions that may not be very strong are cross-validated. So it's very helpful to have a pulsator in a barrier. And to conclude, I would say that you get this consistent detailed model, so it was worth the effort, I think. Let me give here the list of people who worked on this. In green, who got the many spectra that we used, in yellow, actually. And finally, when you want to read the full story, this is the paper from ANDA. There are things I could not tell here. And finally, let me thank the science teams of CoRoT and Kepler for making possible this exciting type of work and the photometric revolution possible. Thank you for your attention.
Thank you, Carla. Comments and questions? John.
Hi, more of a comment. As you showed in the in your light curve, then the eclipses are quite deformed by the pulsations, and of course this gives us the possibility of mapping pulsations on the surface of the stars.
That would be the correct treatment, actually.
Yes, that is something we want to do in the future, definitely.
Yeah, I think, well, for what concerns tidal-induced pulsation, I know that there is the group of Phoebe who is developing some development of the code. But for the rest, there is this mapping by Barnabiro, and that would be the thing to apply. But what I use, of course, is just a first approximation because I don't take into account the mode of pulsation. I just decrease the amplitude of pulsation with phase when the star is eclipsed. That is evidently is not the fully correct thing, but it helps a lot, because otherwise you continue to struggle with, you insert a signal that is not there, taking out the pulsation. That is what happens.
Tim, Betty.
Hi, yes, very nice. You can probably guess what I'm going to ask. Sorry, I'm over here.
I don't see you because so.
Did you try to measure the period spacing of the G modes and make it a shell diagram?
Sorry, if I tried?
Yeah, you could probably guess my question. Did you make a shell diagram and measure the period spacing of the G modes?
Well, there are. I tried to make the shell diagrams, but I didn't find, say, any clear indication. There are a few frequencies. There are 4 frequencies, and then when you put all the 400, it's quite a messy thing.
Okay.
Yeah.
Okay, thank you.
Yeah, for you to do that quickly, Tim, you've got the complication of the eclipses, so the data needs some processing.
The other thing is that you have the orbital period, that is, you have overtones that are in that region.
But, Marc-Antoine, last question.
Do you have an idea of the rotation of...
I try to look for that, actually, yeah. If it's possible to find the splitting of the rotation. In principle, the rotation of the star is low enough to expect some regular splitting, but I did not find, actually it is hidden in the noise, in the many frequencies you have around. It's, I could not, and many of those are probably are fundamental modes. So
but you expect it to be slow rotating from V sin I?
Sorry?
The V sin I is small?
The V sin I is sometimes kilometers per second. I don't remember exactly the figure, but yes, of course you get from spectroscopy, yes. But in the frequency analysis, we did not find the splitting due to rotation, no. Well, of course, you have 2 stars, so you have 2 values, but you assume that you have to look at only at one, even if you are not sure for the lower frequency that they come all from the same star. This is, you can know.
I wanted to just to point that, to recall that rotation affects very strongly the frequency, theoretical frequency. So if it's not taken into account, that can change a lot the conclusion of the seismic study.
I think I did not understand you. Can you tell higher?
Okay. The rotation affects significantly the frequency, particularly in the G mode regime. And if it's not included in the model, the effect of rotation, the conclusion of the seismic study can be very different. That's what I
Okay.
wanted to recall.
But
Yeah,
this is
good
a
point,
slow
Marc-Antoine.
rotator, as we told you.
Okay, can we thank Carla again?